So one of the things that we see a lot is that researchers will try and label a tissue, they'll try and clear a tissue, but they won't necessarily know how to actually image the tissue and acquire the data that they're going after. Each imaging system has very specific use cases where it's great to use that imaging modality and other use cases where it's non-ideal, and understanding those is very important in adopting tissue clearing, because you can go through your whole process, and if you go to your imaging core and they don't have the imaging modality that's compatible with the type of tissue prep that you did, the tissue prep that you did was not worthwhile. So to dive into this in some detail here, when we look at light sheet or confocal or multiphoton microscopy, they all have different use cases. For light sheet microscopy, generally speaking, what it's best for is imaging tissues that are large and imaging those tissues relatively quickly at lower resolution. So we're trying to image a whole mouse brain intact. The approach that we would take is likely light sheet microscopy to do that. You could try and do it with confocal microscopy and dipping objectives, but really the easiest way to do it is to go ahead and do it with light sheet microscopy. However, the problem with light sheet microscopy is that sample prep can be more challenging than it is with confocal microscopy to really match the refractive index, to find the light sheet microscope, as they're not as common as confocal microscopes, and to adopt that into your research project. With confocal microscopes, they're much more ubiquitous. Pretty much every imaging core out there is going to have a confocal microscope that you can use. And confocal microscopes are really best for higher resolution 3D tissue imaging, but smaller volumes. Confocal microscopy also has a tendency to quench fluorophores much more easily than light sheet microscopy, because we're illuminating through the entire depth of a tissue, and therefore generally it's better for thinner tissues than light sheet microscopy, but we're going to get better, crisper images from confocal microscopy. So it's a question of throughput, and also a question of what access do you have at your university or at your company for imaging modalities. If you have an inverted microscope, for example, a confocal inverted or an upright, that'll also change some of the capabilities of what you're able to do. An inverted microscope will only be able to image to a depth of about 1 millimeter into a tissue slice, whereas an upright microscope with dipping objectives can get many millimeters into a tissue depending upon which objectives that you have. So there's a lot of considerations here, but first off, before you dive into any tissue clearing project, you have to look at what types of resources you have access to and see what they allow you to do, because some microscopes will limit what you're able to do as far as tissue thickness, and you should know that before you dive into a protocol for tissue clearing. Now, the way a confocal microscope works is that we're shooting a laser into our tissue off a dichroic mirror. And then what's happening is that laser is exciting a fluorophore within our tissue that we've labeled, and that's coming back through that dichroic mirror, and it's going through a pinhole system. And that pinhole system, what it's doing is it's only allowing light that's coming from the plane that we're imaging at or want to image at to enter into our detector. So this allows us to image an infinite number of planes throughout the depth of our tissue. But one of the problems with this is that while we're only collecting data from a single, very, very thin plane in our tissue, we're illuminating the entire depth of our tissue. So the fluorophores at the top of our tissue will start to quench way before the fluorophores at the bottom of our tissue. And overall, if we're imaging a tissue for a long period of time with confocal microscopy, by the time you get to the bottom of your tissue, or the top of your tissue if you start at the bottom, you're going to have quenched all those fluorophores, and you might not get any signal back from your detector, and that creates a lot of problems with trying to get uniform imaging throughout that depth. So with confocal microscopy, that's always a consideration, is that quenching, and that's why we always suggest using a thinner tissue section for confocal microscopy, because of that effect. To show a little bit more detail on this pinhole element works, because this is the entire background of what makes a confocal, is that while we're illuminating entire depth of the tissue, we're selectively only capturing that imaging plane that matches up with our objective to our detector. And that allows us to get very, very crisp images back to our microscope that we can analyze after we collect all the imaging data from our tissue. There's a lot of principles of microscopy to know, but the most important principle to know is working distance. So working distance is the distance from the bottom of your objective to its imaging plane. And that depth will be the limitation of how far you can get into a tissue. So if your working distance is 10 millimeters, for example, you're only ever going to be able to image 10 millimeters into your tissue. You're not going to be able to go any farther than that because you're limited by that working distance depth. What's really important is as you increase your magnification, generally speaking, that working distance will go down. So for a 40x objective, you might only have a 200 micron working distance that you can work with. So while you'd love to image an entire mouse brain in 40x, you then have to slice an entire mouse brain into 100 or 200 micron sections to be able to do that. So there's some practical limitations associated with just objectives that dictate how far you can get into a tissue. And then field of view. So we look at 4x or 40x, that field of view is 10 times smaller with a 40x compared to a 4x, and because of that, imaging will take 10 times longer in a plane, and will take up to 1,000 times longer in 3D because we have 3 dimensions for that 40x objective compared to that 4x objective. So field of view will dictate how long an imaging run will take for your tissue. And then lastly, numerical aperture is a number that will dictate the quality of the images that you acquire. A higher NA, the better, generally speaking, but high NA, long working distance objectives can be very expensive. These long working distance objectives with high NAs can be $10,000, $20,000, or even $30,000 to image deep into a tissue. So again, that's a reason why many researchers use inverted confocal microscopes with inexpensive air objectives and limit their tissue thickness to 1 millimeter. They don't have to buy very expensive optics just to see slightly deeper into their tissue. Now, I talked about this previously, but the reason that we're not able to see, of course, through our hand is because of differences in refractive index. So all of the cells within my hand have differences in refractive index between the proteins, lipids, and cytosol. And that's what's causing light to diffract and making my hand appear opaque. It's much similar to when I'm looking at a glass of water and I look at a pencil behind that glass of water, that pencil is dramatically distorted because as light's passing through air and then water and then through air, that light is bending and causing that pencil to appear like it's also bent, but it's a refractive index mismatch issue. So refractive index mismatch is what causes a lot of artifacts when we're trying to image deep into a tissue. So we have a tissue that's in an imaging solution that has a similar refractive index, and we have an objective that might not be perfectly matched with refractive index to the tissue and the media that tissue is in. And because of that, we will get differences in refractive index and diffraction that as we get deeper and deeper into a tissue will start to cause artifacts. So our image quality, the deeper we get into a tissue, will start to become worse and worse as we get deeper. So again, this is a reason to keep tissues thinner, so around 1 millimeter or so, which is a practical limitation for many microscopes, and also a practical limitation before you start getting very severe imaging artifacts due to changes in refractive index, specifically if you're using an air objective with deep tissue imaging. So it's very important to understand the refractive index of your microscope objective and trying to match that as closely to the imaging media as possible. Now to show what this looks like, we're looking at a tissue here and we're imaging through that tissue deeper and deeper. And what you're seeing is if we image 100 microns into that tissue, we're getting a slight change in refractive index, and that's causing some distortion. But as we get deeper and deeper, that bending of light as we go from our media to potentially a cover slip to our objective is becoming more and more severe, and because of that, the image quality is reducing the deeper and deeper we get into a tissue. So this is a really important consideration to be aware of when you start adopting tissue clearing into your research, is that while you'd love to get really deep into your tissue, it might not be possible regardless of how clear that tissue is, just because of the objectives that you're working with. So those are the details on confocal microscopy, which I would say is most common. Most researchers that we work with use confocal microscopy, and in our own contract research services, we primarily use confocal microscopy, and a lot of times we use high-content automated confocal microscopy because we can set up many, many 1 millimeter sections of mouse brain tissue or liver tissue all at once, and we can use an automated confocal inverted imager to image all of those tissues for a day or more to collect all of that data, whereas if you try light sheet microscopy, that throughput is going to be much lower, but you can image a larger volume more quickly. So light sheet microscopy, it's ideal for imaging whole mouse brains, and most of the large tissue imaging papers that you've seen use light sheet microscopy. And the way light sheet microscopy works is to pass a very, very thin laser light sheet through your transparent tissue. Laser light sheets are incredibly simple. While these microscopes are not that common, there's not a lot of them out there, and there's few commercial companies that are selling them, light sheet microscopes are actually very simple. You can construct your own light sheet microscope for around $30,000 using the open SPIM resources that are out there. And the technique itself is simple, but it's relatively challenging to get a very thin light sheet through your tissue. But the way we image the tissue using light sheet microscopy is to simply generate this very thin sheet of light and to move that sheet of light through your tissue, which allows us to capture different planes throughout the depth of our tissue, or we can move our tissue through that plane of light. But either way, we're acquiring these steps throughout our tissue and acquiring all those individual slices as we move this laser light sheet through our tissue. It's very rapid. It doesn't cause as much quenching as confocal microscopy, and really allows us to get a very high level of quality through very large tissue volumes. But again, these are not very common. Sample prep is relatively challenging, and these are not able to be easily automated like you can with confocal microscopy. One of the challenges we see from many researchers is the data. So we get through labeling, we get through tissue clearing, we get through the imaging, and then we generate this substantial amount of data. And a lot of researchers struggle with what to actually do with this data, how to process it, how to view it. Many researchers are simply interested in getting some pretty pictures for publication, and that's relatively straightforward. But going ahead and actually analyzing this data can create a lot of bottlenecks for researchers, and that's one of the reasons that when we work with our clients on 3D tissue imaging projects, we stress up front that while we can acquire substantial amounts of data from a tissue, we need to ask ourselves what data is actually meaningful to answer my research question. If I use 4x imaging and that allows me to answer my research question, there's no reason to use 40x imaging that creates 1,000 times more data and will take 1,000 times as long to actually image the tissue. So figuring out up front how much data you want to generate is very, very important to allow you on the back end to actually better answer your research question. For processing the data, we typically process all the individual Z-slices from a 3D imaging campaign individually on their own using tools like Cell Profiler or ImageJ, and this allows us to extract quantitative metrics from our tissues and answer simple questions like co-localization and mapping vasculature and mapping different complex features in 3D. But that will really depend upon your research question specifically, but we always suggest to minimize that data as much as possible on the front end. Now again, interpreting this data is a bottleneck for a lot of researchers. However, there's lots of resources through Cell Profiler and ImageJ that allow you to use open source and free tools to process that data, and there are a number of publications that are out there that allow you to understand which macros and which plugins to use for specific research questions, but this varies from our experience greatly with what a researcher wants to do, from just getting a great three-dimensional rendering to try and analyze how a vasculature network and a brain works. So it really depends on your research question, but we always suggest to researchers to try and dive in first to the free open source tools that are out there. They're a little bit harder to use than some of the more expensive software, but 3D analysis software can be incredibly, incredibly expensive. So we would suggest to dive into those open source platforms first before going into something more expensive like Imaris. Now to wrap up here, we've developed several 3D tissue clearing and labeling kits with Abcam that allow you to easily adopt this into your research workflow without having to go through the process of optimizing the dilution, optimizing the incubation time, and figuring out exactly how to process your tissues. And these kits have been developed for 1mm mouse brain tissues as well as 3D cell culture models to allow you to easily adopt this into your research workflow today. Now, thank you for your time. I much appreciate it.